There are 118 confirmed elements in the periodic table, ranging from hydrogen, the lightest element, to oganesson, the heaviest known. But did you know that every element in your body, from the calcium in your bones to the iron in your blood, was forged in the fiery heart of a star? Welcome to Explore the Curiosity. Today we're delving into the entire journey of star formation. Stick around to learn everything you need to know all in one place. Some elements like hydrogen, helium, and traces of lithium originated during the Big Bang nucleosynthesis, the event that birthed the universe. These primordial elements existed before stars even formed. However, the creation of heavier elements is intricately linked to the life cycles of the stars. Stars act as cosmic factories, where nuclear fusion processes in their cores forge elements heavier than hydrogen and helium. For instance, elements up to iron are synthesized within stellar cores via successive fusion reactions. Supernova explosions and other stellar phenomena play a crucial role in dispersing these newly formed elements into the cosmos. But have you ever wondered how stars themselves come into existence? Join us as we embark on a journey to explore the fascinating birth and eventual demise of stars in this video. The birth and death of a star involves several stages, each characterized by different processes and outcomes. Stars are born within vast clouds of gas and dust called molecular clouds or nebulae. These clouds can collapse under their own gravity due to various factors like shock waves from nearby supernovae or gravitational interactions. So from where do these molecular clouds come from in the first place? Let us explain that in a while, in the later part of the video. As the cloud collapses, it forms a dense core known as a protostar. Gravitational energy is converted into thermal energy, causing the core's temperature and pressure to increase. Surrounding the protostar, a rotating disk of gas and dust called a protostellar disk forms, playing a crucial role in the formation of planetary systems. When the protostar's core reaches temperatures and pressures high enough for nuclear fusion to begin, it becomes a main sequence star. Hydrogen atoms in the core fuse to form helium, releasing energy in the process. This stage can last for billions of years, during which the star remains stable and emits light. Our Sun is currently in this stage, burning hydrogen in its core through nuclear fusion. But this is not the end of it. However, as a main sequence star ages and exhausts its hydrogen fuel, it undergoes changes based on its mass. Low to medium mass stars like the Sun expand into red giants, while high mass stars become supergiants. The Sun, estimated to be about 4.6 billion years old, has approximately another 5 billion years left in its main sequence phase before exhausting its hydrogen fuel. As the Sun continues to burn hydrogen, the core will contract and heat up, while the outer layers will expand and cool, leading to the Sun's transformation into a red giant. Eventually, the outer layers will be shed, forming a planetary nebula, while the core collapses into a dense white dwarf. During the red giant phase, helium fuses into heavier elements like carbon, oxygen, and eventually iron in the core. Low to medium mass stars like the Sun shed their outer layers as they expand, forming a planetary nebula, while the core becomes a white dwarf. High mass stars, however, undergo a catastrophic explosion called a supernova, leaving behind either a neutron star or a black hole. So what happens to a star at the end of its life? The remnants of stellar death depend on the mass of the original star. Let's explore some examples of stellar remnants. White dwarfs. These are the remnants of low to medium mass stars, up to about 8 times the mass of the Sun, after they have exhausted their nuclear fuel and shed their outer layers. White dwarfs cool down very slowly over billions to trillions of years, eventually becoming black dwarfs, cold, dark stellar remnants. Neutron stars. Neutron stars are incredibly dense remnants of massive stars that have undergone supernova explosions. Their lifetimes depend on factors like mass and rotation rate. While some theories suggest they could collapse into black holes, others propose they may dissipate over extremely long timescales. Black holes. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape. They come in different sizes, from stellar mass black holes to supermassive black holes found at the centers of galaxies. Stellar mass black holes can persist indefinitely, while supermassive black holes are thought to exist for the age of the universe and beyond, with some theories suggesting they may eventually evaporate through Hawking radiation. In summary, white dwarfs can exist for billions to trillions of years. Neutron stars can persist for a significant portion of the age of the universe, and black holes can potentially exist indefinitely, with their lifetimes governed by complex astrophysical processes and theoretical considerations. Let us now explain where the molecular clouds come from in the first place. When massive stars reach the end of their lives and explode as supernova, they release enormous amounts of energy and shockwaves into space. These shockwaves can compress nearby gas clouds, triggering the collapse that leads to the formation of molecular clouds. Once molecular clouds form, gravity continues to pull the gas and dust within them closer together, leading to the birth of new stars. Within these clouds, regions of higher density, known as stellar nurseries, give rise to protostars and eventually fully formed stars. This completes the cycle of star formation and death, followed by the reformation of new stars. Do you know what generation star our Sun is? Share your thoughts in the comments below. See you next time.